So it's I mean also this I mean maybe this hour I will go quickly through some topics and maybe we can continue also later on. So but please let me know if this information is okay for you or it is too old, if we should cover it or not. So if you have any feedback, please, it would be very important. So um, so first we need to talk about the four branches of machine learning. I mean there are four branches. We have supervised learning, we have unsupervised learning, we have self-supervised learning, and reinforcement learning. So in supervised learning, in fact, it's the most common use case. This is we just studied machine learning for supervised, in fact, but there are very nice algorithms and very powerful algorithms for unsupervised learning. We will try to cover some of those as well. In supervised learning, it consists of learning to map input data to new targets. We have some inputs. It's like MNIST dataset. We have some inputs. We have a target feature. We have input feature and we have target feature. And we need to create this mapping between inputs and outputs. And it is used for classification and regression. So maybe for classification, we have images, cats and dogs, for example, we need to classify it. We have this iris data set, we need to classify it into three classes. For regression, for example, maybe we want to regress, we want to estimate my income next year based on some information, I mean some historical information collected from the institute, for example. So we can use this one for classification and for regression. And as I told you, when you want to evaluate the model accuracy, maybe you can use confusion matrix in case of classification. In case of regression, we need to use some other accuracy metric. Maybe we can use root mean squared, for example. We have unsupervised learning, and in unsupervised learning, this is a branch of machine learning, which consists of finding interesting transformations of input data without the help of any targets. We don't have any targets. And it can be used for data visualization, for example, it can be used for data compression, because when we use also autoencoder or principal component analysis, we compress data, right? So data compression, it means we try to compress, we try to get rid of some features, for example, so it's for data compression. Data denoising, we can use autoencoder for data denoising, or to better understand the correlations in the data at hand. So if you need to understand the data, maybe you can start by unsupervised learning algorithm. So for example, in iris dataset, we can use 4 target features, and we can start solving it for as an unsupervised. So in this case, we will not use a target feature. Just ignore labels and work with the inputs. So we have A, B, C, and D, for example. So the input to my algorithm will be those 4 inputs, and the output will be a number of clusters. So we need to decide. I mean, it's by domain experts. So I mean, we can find a domain expert who say, okay, this iris flower, we can classify it into 3, 4, or 5. So we need to define number of clusters. And in this case, we can solve the problem as an unsupervised learning. Unsupervised learning, it's the bread and the butter of data analytics, and it is often necessary step to better understand the data set before solving a supervised learning problem. So maybe it could be a step before supervised. So if you want to visualize your data set, if you want to explore the data set, maybe we can use unsupervised learning first. Dimensionality reduction and clustering are well-known categories of unsupervised learning. So if we need to use, for example, autoencoder for dimensionality reduction or data compression, it's unsupervised, it's a feed-forward neural network, in fact, and we train it as a feed-forward neural network using error backpropagation, but we consider it as unsupervised because we are not using the target feature. So the input to the autoencoder will be the features, the input features, but we will not use the target feature. So we will have, for example, some images. We have encoder, we have decoder, and the output from the decoder will be reconstructed image. And the error here will be the difference between the reconstructed image and the original image. We call it reconstruction error. We will use this reconstruction error for going backward and adjusting weights. So in fact, the autoencoder, it's a feed-forward, and we train it as a supervised way. But because we are not using the target features here, we cannot call it supervised. But technically, we train it using a supervised approach. But instead of using the error function, we will have something called reconstruction error. And the error backpropagation algorithm will try to minimize this cost function, which is the reconstruction error. So the next one, it's a self-supervised learning, and in self-supervised learning, it's supervised, it's mixed in fact or hybrid. So it's a supervised learning without human annotated labels. So you can think of it as supervised learning without any human in the loop. So there are still some labels involved, but they are generated from the input data, typically using some heuristic algorithms. For example, predicting the next frame in a video given best frames, or the next word in a text given previous words. Reinforcement learning, this is fantastic, reinforcement learning, because in reinforcement learning, we build an agent, and this agent, intelligent agent, receives information about the environment, and it try to learn how to choose actions. We have set of actions. We have an agent, and this agent receives all information about the environment, like a robot, for example, and it has a set of actions. You need to select one of those actions. For example, you have a robot, and this robot can go forward, backward, left, right. So those are the actions, and stop, for example. So you have maybe 5 actions. You can go forward, go backward, go left, go right, or stop. So the intelligent agent, he will collect all information from the sensors about the environment around the agent, and it will try to select. And I have a function, I have a cost function, in fact, because I need to reach a point. So I have a starting point, and I have my destination or ending point, and I want to go from point A to point B, and the robot should select a good set of actions to reach this goal, maybe as quickly as possible, right? So in this case, we need to design a reward function, and this reward function will try to guide the robot. So for example, a neural network that looks at a video game screen and the output game actions in order to maximize the score can be trained by reinforcement learning. So reinforcement learning is very, very important approach. Types of machine learning problems, there are some types. For example, you can start by binary classification. Binary classification, we have only 2 classes. 1 class and 0 class, for example, and or yes and no, for example. So it's binary classification problem. So for example, spam detection, right? So you got an email and you need to just say, is it spam or is it ham? So it's yes and no. So it's binary classification problem. Medical diagnosis, for example, someone has a disease and you want to say that he has a disease, he does not have the disease. So it's binary classification problem. Credit card fraud detection, for example, it's binary classification problem, yes and no. So binary classification problems, this is very wide. I mean, lots of data are binary classification problems. Cats and dogs, for example, you have an image and you want to say, is it cat or is it a dog, right? Yes and no. Multi-class classification, it's a classification task where each input sample should be categorized into more than 2 categories. It's like iris dataset. So in iris dataset, we have 3 classes. So I have an example, I have a flower, and in this flower, I need to decide, is it Setosa? Is it Virginica? Is it versicolor? So we have 3 classes. So now it's multi-class classification, because each example can be assigned to one of those 3 classes. It's not binary, but it's more than 2. So for example, classifying a set of images of fruits, which may be orange, apples, pears, for example, classify handwritten digits. In handwritten digits, for example, it's from 0 to 9. We have 10 classes. So it's a 10 classes. So each image or each letter should be classified into one of those 10 classes. So in this case, it's multi-class classification. Is it possible to solve a multi-class classification using binary classifier? Yes, it is possible. But we will use multiple of those binary classifiers. So for example, perceptron, the perceptron, we use it for binary classification. But I can use it, in fact, for iris. So in this case, I need a model for each class. So I need to use 3 classes. And each class, in fact, or each model will try to draw a line. It will classify each one against the rest. We call it one versus rest technique. So I will try to plot it here, for example. So imagine that we have a data set like this one. We have here maybe circles. We have here maybe squares. We have here triangles. So do you think, is it multi-class classification or binary classification? You can unmute yourself and just please. So we have this simple data set. So is it binary classification or multi-class classification?
I would say multi-class, but I'm not sure.
Yes, it's a multi-class. This is correct because we have more than 2 classes. So if we need to classify it, how many models we need? And if I will use a perceptron, we know that a perceptron can be used for binary classification, right? And the perceptron, it will, the perceptron usually it will draw a line, right? So it will divide my data set into 2 sections, yes and no, or 1 and 0. So for example, here, if we need to use a perceptron, I can just use a perceptron to make this line, right? So this line, in fact, it will classify this one maybe as 1, or circles as 1 class, and the rest as 0 class. We can use also another perceptron for maybe classifying this one. So it can classify all squares against the rest. I need also another one, for example, and one like this one. So now we have 3 classes, correct? So now I can build a model which can classify my problem correctly using, because it's 1 versus rest. So those triangles, it will be classified versus circles and squares. Those squares will be classified against circles and triangles and so on. So in this case, in fact, we can use a model which is designed for binary classification to solve a multi-class classification. We call this approach 1 versus rest. 1 versus rest. This is very famous technique. And it's very simple. It's just you need to classify each class against the rest. It's supervised, right? So I have all data sets, and I know that I have class 1, class 2, class 3, like Iris dataset. In Iris dataset, we have 3 classes. So I need to get a model for 1 versus rest, for Cytostar versus the rest, for Verticolor versus the rest, and so on. So in this case, I can get this one from a perceptron. I can get this one a model from a perceptron, this one another model from a perceptron, another model from a perceptron. So in this case, we need 3 models. It will be simple, 3 perceptrons for classifying this problem, right? So if I want to draw it, it will be like this one. So I have here 1 perceptron, 2nd perceptron, 3rd perceptron. How many inputs we have? We have 2, for example, or 3 or 4. So if it is like this one, so I will just connect all those. So it will be like this one. This is class 1, this is class 2, this is class 3. 1, 2, 3. So now it's multi-class classification simply. So the perceptron is very effective. In fact, we can use it for solving very complex problems. It looks complex. We need to use feed-forward neural network and error backpropagation, but we can just solve it using a perceptron and perceptron learning rule. Using this smart technique, which is called 1 versus rest. I mean, this is the most simple form. If you want to use feed-forward neural network, we need to add one more layer, in fact. So if I want to use feed-forward neural network, so in this case, we need to add something here to combine decisions, right? So it will be more complex. So binary classification problem, we have 2 classes. For example, we have only circles and triangles, for example, and in this case, we can just simply solve it using a perceptron. But when it's multi-class classification, we have more than 2 classes. So in this case, we need to use maybe more complex models, right? Or we can use number of binary classifiers. How many models? How many binary classifiers? The number of binary classifiers will equal to the number of classes which we have. Because here we have 3 classes, we generated 3 models. We have something else which is called the multi-label classification. In multi-label classification, the classification task here, each input sample can be assigned multiple labels. For instance, a given image may contain both a cat and a dog, and it should be annotated both with a cat and dog label. So the number of labels per each image will be variable, right? So we call it multi-label classification. So we build a system to classify items or some objects, and sometimes we have more than one object in the same image, right? And maybe the same object can be classified as maybe in two classes, for example, right? And finally, we have this scalar regression. We have the scalar regression, and this, I mean, regression. It's simple. The task here, the target is continuous scalar. So I need to predict temperature, room temperature, for example. I want to predict wave speed or whatever. I want to predict stock market price, or so I want to predict income, yearly income, right? So it's continuous variable or continuous scalar. So in this case, we need to build a model for making those predictions. So for example, a perceptron, we can use a perceptron for classification, and we can use a perceptron for regression. If it is for classification, maybe we can use, we will use it for binary classification. So we can use an activation function, which is a step function, for example. We can use a step function as an activation function. But if you want to use it for regression, maybe we can use linear function, right? So so I want to just create a new slide here so I can block it. I want to stop my slides. I want to add one slide, but so okay. So is it possible to just add one slide here? Can you see my screen?
Yes.
Okay, so can you see the news in this empty slide?
Yes, but your old drawings is on top of it.
Okay. So, yes. So discard. So maybe I need to share one more time. Can you see my screen now?
No.
No.
Now you can see it, right?
Yes.
Yes.
Okay. Yeah. So, for example, I mean the difference between classification and regression, for example. So, if you want to use a perceptron is a very simple model. So it will be like this one. Imagine that we have two inputs. So we have here two inputs. Maybe it's x1 and x2, and we need to use here some. We have here summation weighted sum, omega 1, omega 2. We have here bias. We will go back into this into details, and we can just select this kind of. We can select this kind of activation function. If I want to select a different color. So I can use this kind of activation function, right? So the output from this activation function, in fact, it would be 0. Here it would be 0 and 1. So in this case, we can guarantee that the output will be 1 and 0. So I mean, using this kind of activation function, I can solve any binary classification problem. So the difference is very simple. What if you want to use it for regression? For regression, I don't want the output to be number between 0 and 1, or not be just 0, because the output here will be 0 and 1, right? But if I want to use it for regression, so in this case, it will be the same problem. We have two inputs, x1 and x2, omega 1, omega 2. We have here some bias value, right? So, but instead of using this step activation function, we need to use maybe linear activation function. So the linear activation function would be like this one, right? So in this case, the output will be continuous, and it will be just I mean the output here, it would be number between maybe from minus infinity to plus infinity, right? It will be just continuous. So now you can just use it for to regress maybe income, room temperature, for example, right? Wind speed, and so on. So it is the same model. It is the same model. I can use a perceptron for classification. This one we can use it for classification, and we can use this one for regression. So the difference will be that what kind of activation function which we need to use. So the selection of the activation function is very, very, very important. Should we use hard limb? I mean, this one we call it step, and in some places they will call it hard limb. Hard limb. So if we will use this kind of activation function, if you will use hard limb activation function, now the output will be number between 0 and 1. If you will use linear activation function, no, the output will be continuous. It will be number between minus infinity and plus infinity. So we can use this simple model for regression, and we can use this other model for classification. Maybe someone else they will say, okay, what about sigmoid function? Correct? Can we use a sigmoid? So here we have this hard limb function. So the output will be just 0 and 1, right? 0 means it's no, for example, 1 it's yes. So maybe we have here an image, and this image, it's image of a flower from Setosa, for example, from Iris dataset. I have here an image, and I want to classify it. Is it Setosa? Is it versicolor? So when the output is 1, it means it's yes. When it's 0, it means it's no. No means it is the other class, right? It is the other class, which means we can classify. We can. So in fact, when we plot the decision boundary, we will have some data points here. We will have another data points here, and we will draw a line. All points above the line maybe will be classified as 1. All points below it will be classified as 0. So we can use this model to draw a decision line to divide my data set into 2 different classes. Maybe someone else will say, no, I don't want to use this hard limb function, and I want to use sigmoid. So I want to use this function. So I want to use this function. Do you see it? So what will be the output? What will be the value of the output? When we use this function, what will be the meaning of the output? And what will be the value of the output?
Will still be either 0 or 1, right? Or whatever value you assign to h there.
But it will be continuous.
Yeah.
It will be number between 0 and 1. So we will have a continuous scale between 0 and 1. And in this case, we will call it probability, right? So if we will solve the same problem, but instead of using hard limb, we will use this sigmoid function. So instead of the output between 0 and 1, maybe at some point the output will be 0.75, which means it's a 75% probability that it's Setosa, right? So the output will be number between 0 and 1. So it will be probability that this image belongs to some class. And in this case, we can just use a threshold value. So if this number is greater than or equal 0.5, it means it's yes, otherwise it's no. So if you want to solve this problem in different ways, it's not a problem, right? So we will have the same model. You can try to use this hard limb function. And when you use hard limb function, we will use perceptron learning rule, which is very, very simple one to adjust those weights. We need to use this one to adjust those weights. If you will use this function, we will use BLR. If you will use continuous function or this sigmoid function, for example, maybe you can just use something from gradient descent, or because the function is differentiable. This function it's not differentiable, so we need to use BLR. But if we can differentiate this one, in this case we can use gradient descent to change this problem. Anyway, we will have many examples. We will have lots of practical examples to show you the difference between each one. But this is the main idea. There's the same model. We can use the same model for classification. We can use the same model for regression. We can use the model to predict probability. So the output could be just clearly one class 1, class 0. If it is 0 and 1, for example, we can use it for just regression to regress my income next year, for example, right? and we can use it for predicting the probability that specific example belongs to specific class. In multi-class classification, we can use multiple models, one for each class, because we know that each one will draw a line, and we need to get multiple lines to divide my data set into 2 different classes. So we can use this one versus rest, as I mentioned last time. Yes. So do you have any question for that part? Unfortunately, why we have those drawing we cannot get rid of?
So just what you were saying is that the sigmoid function can be used for both the classification and for regression.
Not regression. No, we cannot use a sigmoid for regression.
All right, because it's not. It has the limits. If you want to use a function for regression, there should be no limits, or.
Yes, we need to use linear function.
Yeah.
But
only linear. You cannot use any other function. Like, I mean, how does it affect if it's linear or not linear for regression?
Because I need to keep the output. So, for example, I want to predict the output here. For example, imagine that we have this problem. We have, for example, years of experience. I will just simple example. I will have here years of experience, right? Years of experience, and I in this y-axis here, I will have your yearly income, right? So maybe this income, it will be a number maybe between 500,000 until 2 million, 10 million. So we need to keep the whole range. So if I have a data set, I collect data set from my colleagues from different locations. So I have this as a data set, and we need to create regression line. So we need to get this line. So what do you think? How the line will look like?
Well, you could use different models. For this case, you could use a linear model, but.
So I want to get this straight line, for example. Maybe it will be like this one.
Yeah.
So I need to get this line, right? So what is the equation of this line?
It's a linear function.
It's linear function. So if we have 2 inputs or just we have 1 input, it will be, because here I have only 1 input, which is years of experience. So it will be omega x plus b equals 0. This is correct?
Yeah. So this function is like the fitting function of your data.
Yes. How can we get this function? We can get it from that part.
Okay.
I just need the summation. I don't need the. So I will just use a linear function here. This linear function will do nothing, in fact. So I will get some output here, and this output, the output will be the same. So because this function, this is x and this is y, for example. So y equal x. This function is y equal x. And x equal, it's the summation of omega x plus b. Right? So it will be like this one. Y equal omega x plus b.
Right.
It's equal 0 when we use it for classification, because I need to, but I don't want to do this part here. So it will be just y equal omega x plus b, because I need to use it for regression. So it will be here. If you will use this linear function, so the fit function here, it will be y equal omega x plus b. Now I can make prediction. So I can just say, what if my years of experience is located here? What will be my income? Okay, your income will be this. So just substitute in this equation the value of x. So it will be omega times x plus b. You will get your income, estimated income.
Can I just ask one thing then? But what if you know from like a physical principle that this data that you're collecting should be behaving according to a particular physical principle, and that could be described with a different equation that's not, or a different function which is not linear? You could use that instead, right?
Yes, we here this one is very this domain knowledge. We can call it. It is a domain knowledge, right?
Okay. Yeah.
So for example, you don't want this line to be linear, right? So we want it to be non-linear. So instead of using x, because I know from my my domain expert, I know that your income should be proportional to square of your years of experience. So the curve will look like this. So just instead of using x, I can just use x squared.
Yeah. All right.
So the input here, instead of using x, it should be x squared. So in this case, I will generate a curve, not straight line. Right? So we call it feature engineering. We will have very nice example. In fact, we will have very good example later on. It's one data set, which is we call it circle data set. This circle data set, I have a circle, and all data points inside the circle are, for example, classified as 1. All data points outside the circle are classified as 0. So how can we solve it, right? So I can just if I need to add one more slide, empty slide. How can I clean this one? Okay, clear all drawing. Yes. How can we clean this one? So anyway, imagine that you have a data set like this one. You have a circle. You have some data points inside, and those data points are classified as 1 class, for example. And you have another data points outside, and they are classified as zeros, right? So this is very complex. Can we solve this problem using a perceptron? You know that the perceptron will generate straight line. Can we solve this one using a perceptron? You want?
Sorry, no, I don't think you can, or I don't know.
Yeah, we have two inputs.
Maybe.
Yes, Tarico?
Maybe we have to change the coordinate system.
Yes, this is correct. How can we change this?
Maybe to polar coordinate system.
Yeah, this is very good. Polar coordinates, so we can just measure the distance, right? So how can we do this? It's using
this and the angle, right?
Yes. So there are lots of ways. I mean, if you have some domain knowledge, you can play with those domain knowledge, and it changes the data from this x, y, and x2 into different domain. But one easy way. This one is a circle, right? And we know the equation of the circle. It's ax1 squared plus bx2 squared equal r squared. Correct? Is it correct? Or square root of r squared. Maybe this is the equation of circle, right? So instead of playing with, because if I will build a model, and if I will use x1 and x2, what will happen? This one will generate. If I will use x1 and x2, I will generate a straight line, right? It will be like this one. Let me just draw it with a different line color. So maybe it will be like this one. It's not correct. It will not be able to give me good. Maybe those data points are 1, those are zeros, so it will not give me good accuracy. But if we can work with x1 square and x2 square, we can generate, in fact, this equation of a circle. So in this case, instead of working with a decision boundary, which is a straight line, we can generate a decision boundary, which is a circle, right? We will have this example. So when you are playing with the features, so instead of working with x1 and x2, if you change it x1 into x1 square and x2 into x2 square, instead of generating this straight line, you will generate a circle. And all data points above the circle will be classified as 1. All data points inside the circle will be classified as 0. So we can achieve 100% accuracy if we will do this trick. If you want to solve this problem, you need a feed-forward neural network. You need a complex model, right? Maybe if you don't have enough data points, your model will overfit quickly. But you can solve this complex problem using a perceptron if you can try to modify x1 and x2 into x1 squared and x2 squared. So this is domain knowledge, because you know something about the problem and the data. So I know that it looks like a circle. Now I need to generate a circle. And the omega 1 and the omega 2, it will control the bias here. It will be the radius of the circle. This one, it will control the circle, the radius of the circle. And those weights, if omega 1 equal omega 2 equal 1, for example, it will be a circle. If omega 1 is higher than omega 2, it will be oval, right? You can just change how it will look like according to the value of omega 1 and omega 2. We will have an example in this problem. So as I told you, perceptron is very, very efficient, very, very efficient. In fact, if we understand it very well, and you can just use it for different types of problems and play with feature engineering, so we can make it more simple for the model. And the perceptron, it will not overfit. It's impossible to overfit because this is the most simple model. It cannot overfit at all. And I mean, there's a guarantee that you will get the best results using this. Yeah. So we can go to the next slide. I guess if I need also to remove those drawings, maybe I need to close each time. But so how can I clean this one? You can see the drawings, correct?
Yes. Yes, now it's much better. So can you see my screen?
Yes.
Okay.
Yes.
So we have those 4 types: binary classification problems, multi-class classification problems, multi-label classification problems, and the scalar regression. We need to talk about the model development. There is universal workflow, or they call it pipeline, which we need to follow in order to start working in our problem. First, we need to define the problem. We need to define our problem: how many inputs, how many outputs, what is the goal, which variable which I want to predict or classify, and so on. We need to collect data, relevant data, for example. Maybe if you don't have enough data, maybe you can go for, but it's for the model selection. So if you don't have enough data to train your model, maybe you can go for transfer learning, for example. So I can use a pre-trained model from another problem, another domain, and transfer it to my problem where I have lack of data. You need to choose a measure of success. This is the metric which we need to select. Do you need to maximize accuracy? We need to minimize prediction error, and so on. So we need to select this one if it is classification, if it is regression. As I told you, if it is about fairness, we cannot select fairness. I want to maximize fairness. You need to set an evaluation protocol. So how we will train the model, how we will evaluate my model. Should we go for hold-out validations? Should we go for cross validations? Right? You need to prepare your data. And the first step in preparing your data, you need to visualize your data first. This is very important. I need to visualize my data and understand how my data look like. Maybe if I have different features and the scale of each feature is different. So for example, we collect data for age and income. And if you are living in Norway, income, it's by millions, right? And the age, it's maybe number between maybe 20 and maybe 45, 60, 65. So it's relatively small. Gender, maybe it's 1 and 0, for example. Maybe height, right? If you are collecting heights of people, weight. So the scale of each input will be different. So it's very important to try to standardize your features. I need all my features to be in the same scale. So for example, we can normalize all features. So all features are in the same scale, between 0 and 1, between -1 and 1. It will be very easy for the optimizer or for the learning process that all your features have the same scale. And it's important because of the activation function again, and because also of the nature of machine learning. Because as you can see in the perceptron, we multiply all inputs by some weights, take summations, and apply this number to the activation function. So if those numbers are very big, right, it will be a problem. Some features will have some huge impact on the learning process, and some other features we will ignore it because it will not have any impact. So if we are talking about income and age, if income is a very huge number and the age is maybe 25, 30, for example, maybe the model will try to give more importance to the age, to the income, and ignore other important factors, for example, right? So if I want to I can explain it with a perceptron as well. You have a perceptron here. We have 2 inputs. Maybe this is your income, and this is, for example, age, right? This one has omega-1. This has omega-2. We have here multiplication. We have here some bias, and after that we will apply this one to some activation function, right? So If this one is in millions, so it will be huge big number multiplied by omega 1 plus small number multiplied by omega 2. This number will be applied to this host function to make some decisions. So do you see, in this case, the machine learning model will try to select, it will do some selection by itself. So maybe it will automatically maximize this omega 1 and it will minimize omega 2, which means it will give more importance to the large feature and it will ignore other features. So in this case, the machine learning model will do some feature selection by itself, which is very dangerous. I can do feature selection by myself, but I cannot let the machine do feature selection by itself. Because imagine that we have income, we have age, we have some other variables, and you use those numbers to apply for a loan, for example. So if in the banking systems or in the loan, for example, if they will do this, maybe they will tend to give loans to people who are rich already, who have big income, and they will ignore other people, for example, because they don't consider age, they don't consider other factors. So if we need all variables to be equally to have equal impact, we need to normalize all those features or standardize it, for example. So we need all features to be between 0 and 1, for example. So in this case, all features will have the same impact on my learning process. And technically, it's important because do you see here in this activation function? I mean, the output from the activation function, it's number between 0 and 1. Do you see? So imagine that we didn't normalize, for example. So if we didn't normalize, so it would be big number multiplied by omega 1 plus number multiplied by omega 2. It would be a very, very huge number. So maybe it would be here. It would be converted into 1. So the decision here would be 1. Right? All decisions would be 1 because I have one variable which is very huge. So so it will force my model to select this one. It will focus on this one. This one will have huge impact in the process because all informations will be converted into 1, which might not be correct. So for example, I'm classifying, and 1 means get loan, 0 means you will not get a loan, for example. And if you have huge income here, like in Norway, for example, maybe people have minimum maybe 500,000 income. So in this case, all people will be classified into 1. And we will neglect other important factors. But if we can normalize, all inputs, all features, we will use this part from the activation function. We will use that part. You know this area, and if all numbers are between 0 and 1, so we will play here. So we will keep the diversity of my data set. We will not convert all values into just 1. No, we will keep this continuous range between 0 and 1. Because if your income is for example, the maximum income in my data set is 10 million, so it will be 1. The rest of the people will be in the range between 0 and 1. So in this case, we will keep the diversity of my data set. We will keep the information and the knowledge from the data set. But if we didn't, we will damage, in fact, the data set. Because I didn't normalize, and only just big values will be converted. All big values will be converted into 1. Even the one who is getting 100,000 per year, according to this model here, his values or the model will convert those numbers into 1. So there will be no difference between the one who has 10 million per year and the one who is getting 1 million per year. All people will be the same because those numbers anyways are very huge. But if we can normalize, we will play in this range here. We will have all people represented here, not here, right? So is it clear, or should I say it in a different way? So
I think it's okay.
Okay. So normalization is very, very important. Normalization, we use min-max approach. So we can try to normalize all values between 0 and 1. We have also something called the standardization. So we convert the distribution into normal distribution. So it will have mean value of 0 and variance of 1.
Hello?
So we need to prepare the data. We need to, is there any question?
Yeah.
Yeah.
Can you hear?
Yes.
If we are going to standard each data, for example, we are going to standard each feature alone, individually?
Yes, each column. Each
Yeah.
column alone, yes.
If we are going to do that, will the effect remain the same? For example, if we are standarding the whole data at 1 with respect to some point, maybe we can say that at this the activation point, the effect will be somehow the point, it lies between the 0 and 1.
Mm-hmm.
But if we are standarding each column individually, the effect still remains the same. I mean, I don't know.
Yeah, I mean, this is, I mean, but we can go back to normalization. I know, because maybe if you need to standardize, you need to normalize as well, right? So I mean, we need to and normalization is very important, because I want to play in this area. If I didn't normalize, in fact, we will go here. Maybe we will be here, right? I want to be here, because if I converted all my data points into that place,
yeah,
the decision would be all time 1. So I will not have the chance to cover this area here, right? So we need to be here. We don't need to be here, right? So
okay, thank you.
so because we need to avoid. I mean, if we didn't do this, the neural network itself, it will try to be selective, and maybe it will work anyway. It will work, but maybe we will not discover that there is a problem, right? So it's better to just fix those from the beginning. So we need to prepare data, standardize, normalize, missing values. We need to fix those stuff and so on. Vectorization also. So we need to change. We need to replace all textual values with numbers. We need to divide my data sets into maybe training, testing, validations, and so on. And after that, we need to develop the benchmark or baseline model. We need to start with a simple one, and after that, increase complexity step by step. So it's better to avoid overfitting. So for example, I can start with a very complex model, very huge model, but it will overfit quickly, and you need to simplify it. So it's better to start with a simple model, train your model, and if there is underfitting, you can just increase complexity step by step. So for example, I can add one more hidden layer. I can add more units in the hidden layer, and so on. So start by a simple one, and try to increase complexity with time until you reach the desired or required accuracy. After that, we will use this base model, and we will try to improve it. We will try to tune its hyperparameters and try to make it more, more accurate. And at the end, of course, we need to document our results and the deployment. So we need to, documentation is very important. So what are the information which we need? Maybe some people want to get some, if it is classification problems, maybe we need to compare with other models. Maybe we need to run the model different times, several times, and get average accuracy instead of just accuracy. Confusion matrix, for example, accuracy, precision, recall, and so on. So those numbers are very, very important. You need to also how much maybe it's important for your publication as well. How much epoch? So I trained my model for 20 epoch, for example. How much time it takes? How much memory? What was the speed of my computer? So those numbers are important in your publication. Yes. Do you want to take another break, or should we stop here today and go for project presentations?
I don't know how much you have left for this presentation, but
yeah, I have. In fact, I just need to cover those points here. I mean, how you define your problem. Maybe you can finish it first, and after that we can take a break and go for project presentation. So those points, I will just go into details onto those points quickly. So to define your problem, we have some questions. What is the main objective? What are we trying to predict, for example? I mean, you will define this. For example, today you have a problem, you need to state your problem, you need to start, answering those questions. What are the target feature, for example? What is the input data? Is it available? Do we have enough data? If you don't have enough data, should we try for transfer learning, for example? What kind of problem are we facing? Is it binary classification? Is it multi-class classification? Is it clustering? Is it regression? because based on this, you will select the appropriate model for your problem. Can our outputs be predicted giving those inputs? Do you have enough data to find this kind of mapping between inputs and outputs? Because maybe I'm collecting very, very small data from questionnaires or from something, but it's not enough, in fact, to build the mapping between inputs and outputs. We need to get this meaningful relationship between inputs and outputs. So do we have enough data for doing this? Is the available data sufficient to learn the relationship between inputs and outputs? Is it enough? So you need to define those points. In the data collection part, data collection is a process of collecting and measuring information on some targeted variables, for example, from the system. And it should help us to answer questions and evaluate outcomes. Data sources, there are different sources of data sources. It could be from sensors, from cameras, from surveys, from interviews, from books, from images. The more and the better data that we get, the better our model will perform. This is very important. We need to get more data. I mean, there's one technique called the data augmentation. So if you don't have enough data, we can use data augmentation to enlarge the size of my data. Because if you don't have enough data, your model will overfit quickly. Overfit means my model will not be able to generalize. It will just memorize my data points. So the performance will be very well in the training, but it will not be very good in the testing phase. So, so it's important to get more data. If you don't have enough data, we need to find a solution. So one way is using data augmentation. Data augmentation, it's a technique which is used to enlarge or extend the size of your data set. If not, maybe you can go for data, for example, transfer learning. So I can just get a model which has been pre-trained on a different data set, different problem, but it's close to what I'm doing, and I try to transfer it to my problem. To make some evaluations, we need to select evaluation metrics or measure of success. So, I mean, they say that if you cannot measure it, you cannot improve it. So we need to measure accuracy, for example, or any metric. So we can see that we are okay. We are on the track. We are improving. You can consider, for example, precision, accuracy, recall, fairness, biasness. So all those could be a measure of success. In regression problem, we need to use mean squared error. I mean, we can use those for classification problems, precision, accuracy, recall. But in regression problems, we need to use other metrics such as, for example, mean squared error, mean absolute error, right? In classification problems, precision and accuracy and recall are very well, very, very important metrics. The evaluation protocol, when we train the model, I need to define a good protocol from the beginning so we cannot get any criticized, for example. So we need to measure the progress towards achieving my goal. So how can we do this? We can do, but there are some protocols. I mean, very famous, it's data splitting. There is something called hold-out validations and the cross and the key fold cross validation, for example. In hold-out validation, we split the data into 3 categories or containers, for example, one for training, one for testing, and one for validation. Training data set, we use it for training the model. Testing, we keep it away for testing my model. And the validation part, in fact, we use it for maybe fine-tuning the model parameters and to avoid overfitting in training phase, for example. So in fact, the validation set, you can say that the validation set, it's the testing set of the training set. So if you are dividing your data set, we divide it into 2 big containers, one training, one testing. And from the training part, we need to take 10% maybe for validating the model or for testing the model while it's trained. In k-fold cross validation, we split the data into k partitions or k folds, and we train the model for k-1 and test with k. And we repeat this process k times. And each time we will have some accuracy, and at the end, the average accuracy, I mean, the accuracy at the end will be the average accuracy from those k folds or k times. So we do k-fold cross validation if my data set is very small. So we have a small data set, we cannot sacrifice dividing it, having a testing set, because in the hold-out validation, we hold out one part from the data set. So imagine that I have 100 data points, and I hold out 20 data points for testing. Maybe it's very expensive. So if you are collecting data and it costs you money and it's hard to collect, for example, so it's smart to not use hold out validation, because in hold out validation, we will hold a test set away for just testing. We will not use it for training. But in case of k-fold cross validation, we will use the whole data set, right? We don't hold out any data set. We will divide the data into maybe 5 folds. We will train the model with 4, test with 1, repeat this process 5 times. Each time we will have some accuracy. At the end, we will have an average accuracy. And at the end, you will just train brand new model and just say, okay, this is your model. I will train it with the whole data set with 100 data points. And the accuracy will be this average accuracy, which we got from k-fold cross validation. So k-fold cross validation is very important. And usually when you write a paper, people just ask, why did, if your data set is small, why didn't you use k-fold cross validation? So it's important to use k-fold cross validation, because k-fold cross validation, it helps us to use all data which is available for training and the testing. And the accuracy which we are getting here, it's more robust number, in fact, because it's the average accuracy from 5 different models. And each model will be trained by k-1, tested with k. So in fact, if you select k equal 5, we will build 5 models. Each model will be trained by k-1, tested with k. We will repeat this one 5 times. So we use the whole data set for training and testing. And each time we will have an accuracy. And at the end, we will have an average accuracy. And at the end, I will train the model using the whole data set and just deploy it directly, because we have already now the accuracy. In iterated k-fold cross validation, we do it with shuffling. We just repeat it several times, but we do shuffling each time before dividing the data into k folds or k partitions. So statistically, it will be stronger, in fact, to use iterated k-fold cross validation. In classification problems, post-training and testing data should be representative of my data. So when you divide the data, for example, if we will go for hold-out validation, and I have, for example, I will have this iris data set. I have 3 classes. So the 3 classes should be equally represented in the training and in the testing data set. So imagine that you didn't shuffle the data set, and you selected the first 100 data points for training and the rest for testing. If you look into the table which I showed, which I presented in the last slides, the data sets are not shuffled. So the first 50 points, it's a class 1. The second 50 points are class 2. The last 50 points are class 3. So imagine that I used the first 100 points for training and the last 50 points for testing. It means 2 classes are represented in training, are not represented in the testing. And in the testing set, I have only 1 class, and the other 2 classes are not represented. So this is correct, not correct. So it's very important to shuffle your data several times to be sure that, and when you divide it, you need to be sure that all classes are equally represented in each container, in the training and in the testing. You don't need to shuffle if you are trying to use the best data to predict future. When it's time series, we cannot shuffle it, because if you shuffle, you will destroy your time series. So for example, I have historical data for stock market price, or and I have historical data from 1980 to today, for example. If you will shuffle it, you will destroy your time series. So when it's a time series, you don't need to shuffle it. You just divide. You can just say, okay, I will use the last 20 years for training, and the last 5 years maybe for testing, for example. So in this case, it will work fine. You need to check if there are some duplicates and redundant data in your data set to avoid inaccurate learning, right? They call it information leak. So for example, maybe I have some duplications, and an example was in the training and it was in the testing. So in fact, it will not help me to get accurate numbers, because it was example which has been trained, now it has been testing. So performance will be much better than the actual performance. So it's important that you get sure that I don't have any duplications in my data set. This is how we divide it. So if you have your data set and you want to go for hold out validation, so we will shuffle, right? If it's not a time series, we will shuffle the data, and we will divide it into 2 containers, 1 container for training, one container for testing. If it is k-fold cross validations, and if you selected k equals 3, if k equals 3, we will divide the data into 3 containers, right? And in the first time, I mean for this fold 1, for example, I will train here model 1. So I will start a new model 1, and I will train it using those two and test it here, right? And I will get accuracy from here, so I will just call it accuracy 1. Then I will start a new model here for k equal, this is for k equal 1. So for k equal 1, we will have model 1, we will get accuracy 1. For k equal 2, we will start a new model here, just initialize a new model from scratch, just a brand new model with the same structure, and I will train it using this and this, test it using this one. And from this one, we will get accuracy, we will call it accuracy 2. And for k equals 3, we will repeat this one again. We will start a new model, brand new model called model 3. We will train those models using those, test it with this one to get an accuracy called accuracy 3. So now after k-fold cross validation, I have 3 models and the 3 accuracies. Should we use one of those models? No, we will not use any of those models. We will get average accuracy. So we will just we are interested in the accuracy. So we will just say that average accuracy will be AC1 plus AC2 plus AC3 divided by 3. So this is my average accuracy. And start a new model from scratch with the same structure, but it's initialized from scratch, and train it using the whole data set. So I will train this model using the whole data set. Do you need to check accuracy? No, you don't need to check accuracy because you don't have data for this, in fact. And I already checked this, and I have this average accuracy. So this model will have this average accuracy. So this is k-fold cross validation. So do you have any questions for, I mean, the difference between hold out validations and the k-fold cross validation? Any questions? We will do this. I mean, we will repeat this one during this course. We will repeat this one several times, but this is very, very important to know the difference between hold out validation. You can go for hold out validation if you have, for example, 10,000 data points or right. So it's big number. So now we can sacrifice this hold out validations, right? We can divide it into 80% for training, 20% for testing, because 80% will be huge. It will be very enough. But if you have a small data set like 100 points, 1,000 points, so don't go for hold out validation because it's too expensive for us. We don't need to hold out any data for testing, and I need to use the whole data set. So in this case, we can go for k-fold cross validation. And as you can see here, at the end, I built a model with the whole data set. We didn't sacrifice any data points. We didn't hold out any data points. I trained the model using the whole data set. And I have an average accuracy, which is more accurate in fact, because I mean, how we get those average accuracy using k-fold cross validation, it's more statistically more correct, more significant. Data, do you have any questions for that part? Any questions?
I can ask one question. So in my case, if I'm measuring waves in a wave tank and I have a measuring or a sensor frequency of 0. Or 1 hertz, I don't know. Yeah, and I measure it for a long period of time. I get a lot of data points, and I want to predict, or I want to make a model of this. Then I would use this. I would not use k-fold because the data set would be too large, right?
Yes, yes. So if you have 2 big data sets, you don't have this problem. We just use the k-fold cross validation when it because this one takes time. Can you see here? In fact, when you I mean, see, because we have trade-off between time and so I mean, hold out validation. It's more simple. We will train one model and we will test it, right? But here, in fact, when we select k equals 3, we build the 4 models. So it takes more time. And if your data set is big, it will take more time to train each model.
Okay, yeah.
We just go for this k-fold cross validation when we have very small data set. And then when it's a small data set, anyway, the model will be trained quickly. So it will not be time consuming for us to use k-fold cross validation. So you can just go directly for hold out validation.
Yeah. Okay.
Yes. Any other questions? Yes. I mean, data preparation, we talked about it already. So we need to process the data to make it more suitable for neural network, right? And it includes the vectorization, normalization, handling missing values in feature extraction, for example. So missing data, I talk about it. We need to eliminate features with many missing values, with the risk of losing some important information, right? So, for example, if I have a feature such as age, and not all customers they have written their age, for example, so I can just say, okay, I will remove age. But maybe removing age is very critical. So imagine that it's a fashion. We try to design new clothes or product, for example, and we need to target some specific user groups or customers. So maybe age is important. So if you want to remove any, I mean, you need to measure the risk. If you will eliminate any feature, you need to measure the risk. Is it really important to? Can we remove it or should we keep it? So it's a decision which you need to take, in fact, because maybe I will just say, okay, I will just it's headache and I will just remove age. No, but age is important for this problem. You cannot remove it. So in this case, we need to fill in those missing values. How can we do this? Maybe by just estimates. Take the mean value of the rest of the samples and just fill up those missing values with this estimates, for example. So this is one way for doing it. Imputation, we call it imputing. So we call it data imputation, in fact. So when you replace those missing values with some numbers, we call it data imputation. And the imputation techniques, there are many tools in Python, for example, you can do it quickly in Python. So you can just fill up all those missing values by average or by mean value, or yes. Data vectorization, we need to handle categorical data. So for example, if I have a data set, for example, we have fruits, we have some, for example, red, green, blue, in my target feature, I can just replace each one with a number because we cannot work with categorical variables. We need to convert it into numerical values. So for example, I can replace red with 0, green with 1, blue with 2, for example. In this case, I will change my data set into numerical value, which is suitable for machine learning. Feature scaling. This one is very important because sometimes in data sets you have, for example, sex, and it's male, female. So I need to replace male maybe by 1, female by male by 1, female by 0, or otherwise, correct? So this is very important. Feature scaling. So it's important for the learning algorithm to perform much better when dealing with features that are on the same scale. Because if we didn't do it, in fact, maybe we have the risk is that neural network will do feature selection by itself, and it's very dangerous because you will not discover that there is a problem. In fact, maybe they will discover it after some years. So imagine that you are building a system for a bank, it works fine, all numbers on paper is perfect, and after maybe 10 years, the bank will go bankruptcy because because the model is not fair. In fact, so I want to get a loan, they say no, so I move to another bank, right? So it will be easy for people to get loan, not easy for other people to get loan. Maybe customers will be not satisfied, and they will just move to another bank. So they will discover it in the hard way. So normalization, we need to rescale the features to the range between 0 and 1. Standardization, we need to center the features at mean 0 with standard deviation of 1. And there are some equations, and it's very simple. So for example, if we need to do some normalization, so x normalized would be x minus x minimum divided by range, or x max minus x minimum. So we need to do it column by column. So you just need it and just repeat it for each column. If it is normal standardization, so it would be x minus mean value divided by standard deviation. We will do it also column by column. Selecting meaningful features, sometimes you have redundancy, you have some duplications. So it's important to select the most important features. Maybe if you are a domain expert, you will just do it by yourself. Otherwise, you can use some tools, for example, for helping you. We can use principal component analysis, but principal component analysis, we use it for feature, for dimensionality reduction. And compression, data compression. There is a tool, very nice tool in Python. called select k-best, and it's based on a statistical background, in fact. So they try to find the correlations, and it will give you maybe most correlated features with the output, with the target feature. So select k-best, it's a very nice function in MATLAB, in Python, in fact, which we can use it for feature selection. We have also autoencoder, and the autoencoder we can use it for. We can use the autoencoder for dimensionality reduction. We can use it for denoising, for example, data compression. So so autoencoder it's straightforward in neural network. It consists of coder and the decoder, right? We train it. We are more interested in the coder, so not in the decoder, right? So we train the model. It consists of two parts, and after training it, we will just use the first part for data compression. And then, of course, the data splitting. And the data splitting, we'll talk about it already. If we will go for hold-out validations, or if you will go for k-fold cross validation. So this data splitting, it's based on the amount of data set which you have. You can just decide. And after that, we need to develop baseline model. And this baseline model, we will just use, we have X and Y now. We have X, all X's will be the input features. Y will be the target feature. So now I have my data set as a table. Maybe those input features will be images, maybe text, maybe anyhow. So we will use those data for building a basic model. Baseline model, simple model. So we need to start with something simple, and after that we try to improve it to adjust accuracy. And instead of going for very complex one and try to fix it. So it's much easier to start with a baseline model, and after that try to fine tune it. The goal is to achieve model that can generalize, which means it can perform well on never before seen data, right? So this is very important. So in this case, we split the data into maybe 3 sets for hold-out validations, training, validations, and the test set. In the training, we try to adjust weights, and in the validation, we try to fine-tune the model and discover if we have any overfitting problem. And from the validation error and the accuracy, we can discover overfitting during the training phase and use techniques such as, in overfitting, it's a problem. And there are lots of techniques which we can use, in fact. So we can use early stopping to stop training and don't overfit the data, for example. We can use, we can try to reduce model capacity using the dropout and stuff like this. So in testing, we measure the generalization power of your model. We try to avoid overfitting and minimize, maximize, in fact, the generalization. We use test set to evaluate the final model. So if the model overfits the data when it has high model capacity or little data. So if you have overfitting problems, so we need to check. Maybe your model is very complex, which means it has huge capacity. So there is no chance it will just memorize your data sets quickly. So in this case, we need to reduce model capacity. And maybe also your data set is very small. If your data set is very small, maybe there are 2 ways. You can use k-fold cross validation, and maybe you can use data augmentation. Maybe also you can just transfer a model from another problem into your problem. Overfitting and afterfitting. This one, it's underfit. I have a data set, and we will try to make a model, for example, to maybe predict or regress something. So it looks like overfitting. It cannot capture underlying information from my data set. Maybe this one, it's a good fit. Maybe this one, it's overfitting my data points. When it's overfitting, it try to learn noise in the data and try to, in generalization, it will be a very bad model, in fact. So this one, it's overfitting problem. It's a very complex one. And as I said, overfitting, it's maybe because of model capacity. I select very, very complex model. So the very complex model, it will just memorize my data points very quickly. So in this case, I need to reduce the model capacity. To improve, so we call it generalization. It cannot generalize. And to improve this problem here, to fix this problem here, maybe we need to get more data because my data point is very, very small. I need to get more data. Maybe I need to add some weight regularization using L1 and L1 techniques. So it's like adding some limits on the value that a weight can take. We can use techniques such as early stopping. And if you need to use early stopping, you need to have a validation set. to discover that we are overfit, right? Model reduction to reduce model capacity, dropout techniques. So there are main techniques which we can use. I mean, if you are working in Python, those are already there. You just need to activate it. You just need to select it. So if you want to use dropout, for example, you just need to select it. We will have some, and of course, select something called dropout ratio, for example. So dropout, it's already there. Early stopping also, you just need to activate early stopping. So when the model starts overfit, it should go back to maybe one previous or two previous epochs. And finally, developing a model that does better than the baseline. And after having your baseline model and you are happy with the performance, you can just try to fine-tune this model to get much better model. How can we do this? Just to try to improve, try to select different activation functions, try to select different loss functions, for example. So in order to improve the base model which you have already in place. Maybe you can just stop here, right? And you can just take a break, maybe for 10 minutes. But first, do you have any question for that part? Any questions? Okay, so we will stop here. Maybe we can take 10 minutes break, and we can start 11:30. Maybe you can just have maybe 2 presentations today, for example. 2 or 3 presentations, we will see who want to present today. And we will finish today at 12, and we will continue next week. Maybe also, I will try to cover some points, and at the same time, you will present your project, and you will start working in your project as well. So now we will have a break for maybe for 10 minutes. We can start at maybe 11:30 or 11:35. We can just have maybe 2 presentations or 3 presentations. People can present their project, and they can get also some feedback from